Good morning students. Today we are going to discuss about the pressure exerted by a gas. This derivation we are going to derive that. So the expression for the pressure exerted by the gas. Consider a monoatomic gas. So it will be placed in the 1 cubical cylinder. So consider this is the 1 cubical cylinder. Consider this is the 1 cubical cylinder. This cubical cylinder having length or side L. So each and every side, cuboid means each and every side will be same only. So each and every side the length is L. Okay. So it having monoatomic gas like this. So that gas having so much number of molecules. So this molecules always moving in a random manner. Okay, randomly it will be moving all the direction. This molecule may be this direction and this direction. Okay, so randomly it will be moving in all the direction. Okay, so suppose if this molecules moving random direction and will be hit that walls. So consider this the one wall. Suppose if the molecule hit that wall, okay, there is no loss of energy because that collision between walls and molecule is elastic. Okay, so already we discussed in 7th chapter elastic property. So this molecules having elastic property in nature. Suppose if the molecules collide with each other, okay, there is no loss of energy, but there only it transfer their momentum. If the molecules, so this is the one molecule, this molecule hit the walls of the container, okay. It hits the walls of the container, only it transfer their momentum, not transfer their energy. After hit that walls, it will be reflected back. Okay, so it transfer their momentum. What is that momentum? Momentum formula P is equal to mv. And next, if some other molecules, okay, so other molecules also keep the walls of the container, it also transfer their momentum, okay, at a particular interval of time. That particular interval of time is del t, okay. So that momentum is continuously changing in that wall. That momentum is continuously changing in that wall. So at a particular interval of time, that momentum is continuously changing. Okay, if the momentum is continuously changing with a particular interval of time, okay, that is called as a force. So this wall experienced some amount of force. Okay, so this wall experienced some amount of force according to Newton's second law. The rate of change of momentum is directly proportional to the applied force. So when the changing momentum with a particular interval of time, it will be experience some amount of force. Okay. Then next, consider this is the 1 unit area. Consider the wall in walls. This is the 1 unit area, that is A. Okay. If the unit area experience how much amount of force per unit area, experience how much amount of force, that is called as a pressure. So pressure is equal to force per unit area. Okay, so do you understand, ma? So continuously that molecules are moving random in all the direction. It will be hit that walls of the container. There is no loss of energy, but it transfer their energy but it transfer their momentum. Continuously hit the walls of the container means that momentum will be changing at a particular interval of time. It will be experience some amount of force per unit area. How much amount of force the wall experience, that is called as a pressure. Okay, so this pressure we are going to find out. Okay, so this is the pressure exerted by a gas. So this pressure will be considered only one molecule. Okay, so gas having so much number of molecules, but I am going to derive that derivation for only one molecule pressure exerted by the molecule on that wall. Okay, per molecule how much pressure exerted on that wall or container. Okay, do you understand, ma? Okay, then next, so I already told that molecules are randomly moving, it having elastic property in nature. Okay, so randomly moving means what is the direction? So we have three directions in Cartesian coordinate. We have three directions. One is the x direction, y direction, and z direction. Suppose if the velocity, if the molecules or particle moving x direction, it having the velocity vx. Suppose if the molecules moving in y direction, that molecule having velocity vy. Suppose the velocity of the particle moving in a z direction means this is the vz. Okay, so we can take the three direction x, y, and z. If the particle moving in the x direction, the velocity of particle moving in x direction, we can take that vx. If the particle moving in y direction, the velocity of particle is vy, and if the velocity of particle moving in a z direction, that is vz. Okay, now I am going to consider only one molecule that will be moving x direction. So this is the one walls of the container. Okay, so this is the one walls of the container in x direction, this is the y direction and z direction. So this, consider this is the one molecule. This molecule having that momentum mvx, because that molecule, each and every molecule having mass also. Okay, so this molecule having mass m, it will be moving in a x direction, it having velocity vx. Okay, and it will hits the walls of the container. What happened? It transfer their momentum and also reflect back. Okay, it transfer their momentum and also reflecting at the back in negative x direction. Okay, after a reflection or after bouncing back to the negative x direction. So it having, that is it having that momentum is minus vx, because this molecule moving in a positive x direction, after reflection or after bouncing back to the walls of the container, it having negative, it is moving negative x direction, so that is minus mvx. Now I am going to calculate that changing momentum. Changing momentum is equal to changing momentum is equal to, that is P is equal to del P. You just name del P or P, just you can put a P. Changing momentum P is equal to final momentum Pf minus initial momentum. Changing momentum is equal to final momentum minus initial momentum. What is the final momentum? This is the initial momentum mvx. Okay, before reflection. Okay, that momentum is initial momentum mvx. After reflection, it having that point after collision. After collision between the molecules and walls, it having the momentum minus vx. So final momentum is minus mvx and initial momentum is plus mvx. So here minus sign is there, so minus mvx x. Okay, so totally we can get minus 2mvx. Okay, the changing momentum is equal to minus 2mvx. According to consideration of linear momentum, you can take that 2mvx. From consideration of linear momentum, we can modify this equation. We can get 2mvx because minus 2mvx and plus 2mvx. So after collision, the total momentum before collision is equal to total momentum after collision. Okay, so they both are equal only. So only I can take that 2mvx minus sign, you can just omit it. Okay, then next, so this is the changing momentum. This for only one molecule. Okay, next, number density. Number density is equal to total number of molecules per unit volume. That is called as a number density. Okay, so this is the one cubical cylinder. This is the one cubical cylinder. This cubical cylinder having n number of total n number of molecules, total number of molecules. Okay, so this molecules all hit that any one side of the wall. For example, I can take that positive. This is the right side of the wall. Okay, in right side of the wall, how many number of molecules hit that? How many number of molecules hitting? Okay, or how many number of molecules hit the right side of the wall? We have to calculate. So that number of that is, you can take that small n. So that small n represent the, okay, that small n represent the number of molecules hitting on the right side of the wall. That's equal to, you can take that n by v. So this is the total number of molecules per unit volume. So per unit volume, okay, so per unit volume, how many number of molecules are hitting? That is called as a n, small n. Okay, so small n is equal to number of molecules hit the right side of the wall per unit volume. N is equal to n by v. Then distance. What is the distance? Here this is the distance. So distance you have to calculate. So how to calculate the distance? Velocity of that molecule is Vx into time interval del t. So that is called as a distance. So each and every molecule covers the distance is Vx into del t. Okay, each and every molecule covers the distance is Vx into del t. So velocity is equal to, what is the formula? Distance divided by time taken. So distance equal to velocity into time taken. So here velocity of that particle moving in a right side of the wall. So we can take that Vx into time interval del t. Okay, so this is the distance. Then this is the volume. Totally how much number of molecules are hitting that wall. Okay, so number of molecules are hitting the wall, the volume is equal to the number of molecules the number of molecules hit the right side of the wall. Right side of the wall is equal to number density, because per unit volume how much number hitting, okay, we want to find out. So only you can multiply with the number hitting density, number density into volume. Okay, for example, suppose 2 unit volume is there. Okay, so 2 unit volume is there. 100 molecules are hitting per unit volume, that means 1. So totally how much number of molecules sitting in the wall is 200. Okay, do you understand? So per unit volume 100 molecules are hitting. Okay, suppose the volume of the cylinder contains 2 unit means you can just multiply them. You can get the total number of number of molecules hit the right side of the wall. Okay, so number density into volume. But number density is equal to n. It's just you can take that n. And volume is equal to what is the formula? Area into distance. So area A and distance. What is the formula we found that? Distance is equal to Vx into del T. Distance equal to Vx into del T. Okay. So NaVx into del T. NaVx into del T. Okay. Then next, so this cuboid. Okay. This cubical cylinder. If is it all that molecules are hitting on the right side of the wall at the same time? No. Okay. So some of them will be moving hit the wall and some of them back into the wall. Okay. Or after collision, before collision, some of them all hitting the wall or some of them moving out. Okay. And some of them going into the wall. Okay. So we can calculate that average velocity. Okay. So we have to calculate the average. So average number of molecules. Average number of molecules you can take that n by 2. So the right side alone. Okay. The number of molecules hit the right side of the wall alone. We can take that n by 2 n by 2 A Vx into del T. N by 2 A Vx into del T, because some of them moving towards that wall and some of them hit the wall and some of them back to the wall. Okay, do you understand? So we want to find out, we can calculate the average number of molecules hit the ground. Okay, hit the wall. Okay, so how much number of molecules hit the ground? Average means you can take that for some, you can take that 2 direction. One is moving right side and another one moving left side. So total number n. So only you can take the two sides. One is moving right side and another one is moving left side. So you can take that average n by 2. So the number of molecules hit the right side of the wall is n by 2 is n by 2 of A Vx into del T. Okay. Then next, momentum. Momentum you can calculate. Momentum is equal to, what is the formula? Momentum is equal to mvx. So we already discussed the total changing momentum is equal to 2 mvx. So this is for only one molecule. Okay, per molecule that momentum P is equal to 2 mvx. Totally, how much number of molecules hit the right side of the wall? It is n by 2 A Vx into del T. Okay, so total momentum of the right side of the wall is number of molecules hit the right side of the wall into per unit per molecule momentum of per unit molecule. So P is equal to n by 2 A Vx into del T into 2 mvx. So here 2 and 2 cancel. We can get n a m. Here Vx is there. So here also Vx. So Vx squared n a m Vx squared into del T. Okay. So the total changing momentum is equal to n a m Vx squared into del T. So the total changing momentum P is equal to n a m Vx squared into del t. Okay. Then next it will be experience the force per unit time. It experience some amount of force. So that force is equal to changing momentum divided by time taken. So this is the changing momentum del p. Okay. So changing momentum. What is the formula? N A M v squared x into del t divided by del t. So this del t and del t cancel with each other. We can get N A M v squared x. So the force experienced by the right side of wall of the container is N A M v squared x. Okay, the force experienced by the right side wall of the container is N A M v squared x. Next, going to calculate the pressure. Pressure exerted by the walls of the container is pressure P is equal to, what is the formula? Force per area. So force per area, force is equal to N A M v squared x divided by area A. A cancel, can get P is equal to N M v squared x. So pressure is equal to, here this is the momentum and this one pressure. Okay, don't confuse it. So this is the pressure is equal to force per unit area. So A all divide panel, we can get P is equal to N M v squared x. Okay. Then next, the molecules are randomly moving in all the direction. Okay, so all the direction we can calculate that average velocity. Each and every molecule cannot having the same velocity. Okay, some of them having speed highest velocity, some of them having least velocity. So each and every molecule is having different velocity. So we have to calculate that average velocity. So v squared x you can replace by v squared bar x. So this is called as an average velocity. So pressure exerted by the case P is equal to N M v bar square x. Okay. So it will be moving randomly all the direction. So it having v squared x and v squared y is equal to v squared z. All the direction having same velocity. You can negligible the acceleration due to gravity. Okay, so gravity you have to neglect that, means we can the velocity, the magnitude of velocity is same for in all that direction. Average velocity, the average velocity is same for in all the direction. So v squared x equal to v squared y, v bar squared x equal to v bar squared y is equal to v bar squared v z. Okay, so average velocity is equal to v squared is equal to, so v x squared plus v y squared plus v z squared divided by 3. Average, you have to calculate the average, total average velocity. So you can sum up all the 3 average velocity in all the direction divided by 3. Okay, so here all are same. So v bar squared is equal to 1 by 3 v bar squared, not average. So you can sum up all that velocity is equal to, so v bar squared is equal to vx squared is equal to v squared y plus v squared y is equal to v squared z. So you can substitute v squared y by v squared x and v squared z by v squared x. So you can get 3 v squared x. Then v squared x is equal to 1 by 3 v bar squared. Okay, so v squared bar x is equal to 1 by 3 v bar squared. Now you can substitute that in this equation. So p is equal to n m v squared x you can replace by 1 by 3 v bar squared. 1 by 3 v bar squared. Okay, or P is equal to 1 by 3 Nm V bar square. Here N is the number density and M is the mass of that molecule and V bar is the average velocity in all the direction. So all the direction if the gas is moving, so this is called as a pressure exerted by the gas. Okay, so P is equal to P is equal to 1 by 3 N. Number density, you can substitute capital N by V, that is the total number of molecules per unit volume into M V bar square. Okay, so N by V. So P is directly proportional to N by V. First case, the number density. When you increase the number of density, pressure is also increasing. Okay, when you increase the number density, the pressure exerted by the gas is also increasing. Then second case, P is directly proportional to M. So mass is directly proportional to pressure. If you increase that mass of the molecule, okay, if you increase the mass of the gas, the pressure is also increasing. Then third one, P is directly proportional to root mean square. This is called as a root mean square. Okay, so this root mean square is also when you increase the root mean square velocity of that particle or molecule, the pressure is also increasing. Okay, you understand, ma? And next we are taking that cubical container. Okay, suppose if you take that rectangular container or any shape, if you take that, means that pressure exerted by the gases, again this same formula only we can get, because here there is no area. If any area is there, so pressure exerted by the gas is independent of independent of area. Okay, whatever area you can choose, that the pressure exerted by the gas is same. Okay, so pressure exerted by the gas is independent of area. Okay, ma'am, do you understand? Okay, thank you.